Hello everyone, welcome back to my channel. So this is the third part of graph data structure. So far we have covered up until breadth first search and graph data structures. So in this video I'm going to cover DFS, which is also known as depth first search. So if you can recall, breadth first search was something that you will have to explore each neighbors first before moving on to the next neighbor. Now, in DFS, depth first search, as the name says, you have to go to the depth of the graph. So before going to the next branch, you will have to completely explore the entire branch. Uh, so let me give you an example. So let's say you are in a maze or you want to find a way out. You will start at the entrance, right? And then you will decide to explore every possible path as deeply as you can. So you'll be like, okay, I'm going to walk until I find the dead end. At each junction, you choose a path and follow it until there is no other way to go out. I mean, you will reach a dead end or the exit. So if you hit the dead end, what are you going to do? You are going to backtrack. You're going to go back to the last junction and you'll have to explore a different path. So in depth first search, this is exactly what we do. We start at the node. So node is entrance. You'll have to explore one path fully until you reach the dead end. And when we can't go any further, and we'll have to go and backtrack to explore other paths. So this is the definition of depth first search. Let's go to the whiteboard and then we'll see how it actually works. And we'll also write pseudocode. And after understanding the pseudocode, I'm going to walk you through the entire Java code of this implementation. Okay, so as we can see that I have just taken an example from website from. Okay, so now we are going to see how this works. And here is an example that I have taken from one of the websites on the internet. So as you can see, it's a undirected graph, so we don't have to worry about directions for this particular case. Uh, Now, in DFS, as we discussed, we'll have to go to the depth of the graph, right? So now what we have to do, let's say we are starting from one. Okay, so we have started from one. So now I'm going to print one here. Okay, so we are starting from one, and I'll have to see, okay, what are the neighbors of one? We have neighbors two and we have neighbors zero. So you can go with either of them. I'm going to go with zero. So let's say I have added zero here. Now I'm at zero. So now zero is going to see what are my neighbors. I only have two neighbors, one and two, and one has already been covered. So now I only have one option. I have to go to two. There is no other way I can go anywhere else. So I am here at two now. So now two is going to see what are my neighbors now. Okay. So my neighbors are 1, 0, 1, 0, and 3. All others are covered. So I also have 4. So I can go to either of them. Let's say I would choose 3. So now I am at 3 right now. So now here's the tricky part, right? I am at 3 right now. So I'm going to assume that I don't have any other neighbors because I don't have anything connected to me. If I'm going to find destination, if I'm going to find the edge of my node, I'm not going to find anything with 3. So it is going to say, okay, no, sorry, my bad. It has a neighbor, it has a 2. So, but it doesn't have any other neighbor which is not being covered. Okay, so it's going to backtrack. So what do we do in the backtrack? We will go to the previous element. So it went to 2 to 3, right? So now it is just going to it is just going to go back to 2. So now it is up to 2 that, okay, what are my neighbors now and which one is left? So all of them are covered. Only 4 is not covered. So I'm just going to add 4 in my implementation. And in this way, all of my elements are now covered. Okay, so now the question is, how do we implement this on a code? So it's a very, very simple implementation. It is just a matter of 3 steps. So first step is I'm going to have this current node and I'll just print this current node like this. And then I'm going to make my visited array at current element, visited array at current element is equals to true. So if I do that, visited element at current is true. So I have a Boolean array that we discussed. We discussed in our last video that we do have to create Boolean array every time to keep track of which nodes are covered and which nodes are not covered. So it is very simple thing that you have to make sure if the current element is true already, then there is no point of even visiting that node because that has already been covered. Okay. So now you are at visitor current is equals to true. And now what is the next thing that comes into the play? We just have to see what are my neighbors and how do we actually explore the neighbors in our graph. So what do you need to do? You'll have to find edge. Okay, so how do you find edge in graph? It is how do you find the edge in the graph? It is just like current element dot get I, and you have to implement this step inside the for loop that goes from the first element to the last element, which will be the size of graph, and you have to do I plus plus every time. So once you have done that, now you will know what are the neighbors. How do you access the neighbors? So if I have the edge, so whatever the destination, whatever the e dot destination is, that is going to be my neighbor. So let's say I'm going to, my current element is this right now. Okay, so I'm at one right now. And at the very beginning, I'm at one. So I have I'm getting this edge E is equals to, sorry, it's getting very ugly right now. Okay, let me rewrite that. So let's say I have edge E is equals to one. So now what is going to be my E dot destination? My E dot destination is going to be 0. And now if I do this thing recursively every single time I run the function, it is going to explore the neighbors one by one. And in this way, I am going to explore everything that is inside my graph. So I hope that this made sense. Let me walk through you to the code, and then I guess you guys will have better understanding of what I'm trying to say. So here is my code. If you can see that it is very, very similar to what we had in BFS, breadth first search. The only difference we are going to do is that instead of exploring all the neighbors first, we are going to the depth. Uh, and we are implementing DFS for that, right? So if you would notice that everything is same, this create graph function is also same. We have discussed this already in my last video. Just to give a quick recall, what are we going to do? And we are going to implement the adjacency list for this. And for that, we can also say that we are making lists of lists. Inside our edges, we will have to implement source destination. And in case if it is a directed graph, we are going to need weight as sorry, in case if it is a weighted graph, we are going to need weight as well. So this is just the basic implementation that we have covered already. So now here is the only change, and that is the DFS function, right? So inside our DFS function, we are going to pass a graph into V, which is going to be the index of our visited array, Boolean visited, that is my array, right? So first of all, as we discussed, we have to make sure that it is visited already. So we will have to make it true first, and then we have to print that element, and then we'll have to go and write it down, and then we'll have to go and reach to the e dot destination, right? And what is e dot destination? E dot destination is my neighbor, and then we'll have to make a recursive call so that the same thing happens, but the same thing happens with the neighbors. So for example, I am at 2 right now. Okay, so if I want to go to 3, what am I going to do? 3 is so if my edge is at 2 right now, if my edge is at 2 right now, then 3 is going to be the e dot destination of 2. So now I'm at 3 right now. So if I make a recursive call, it is going to do the same thing for 3 as well. It is going to reach to the neighbor of 3, and it's going to check if the visited element, if the visited current is true or not. And if it is not true, then it is going to go backtrack, and then it is going to explore the same thing for the other elements here as well. So this is how we can implement this. uh, I assume that BFS is kind of tricky, if in terms of code, because it also includes a queue data structure, and then we'll have to implement it using the Boolean array and all that. But with the DFS, it's a simple thing. We just have to do a recursion, and then everything will go very smooth. So this is how we can implement it using recursion. And this was everything for this third part of the graph data structure. Thank you so much for watching, and stay tuned for the further videos of this graph data structure. Thank you so much.